So it's a great pleasure to introduce again Philipp. Let me get this chair out of the way so you don't. Philipp's been doing a lot of really interesting work in the area of, I guess you guys seem to be calling it Bayesian numerics.
Probabilistic numerics.
Probabilistic numerics, which is a lot of numerical algorithms implicitly have sort of functions underlying them. So if you think about numerical approaches, for example, to solving ordinary differential equations, you're trying to find a functional solution. And actually these algorithms are typically making assumptions about the form of that functional solution. Like Runge-Kutta makes a polynomial type assumption, doesn't it? Something
Maybe.
of that form. And it's often not clear that they're doing, that they're making these assumptions, or spline assumptions, or whatever. Personally, I characterize probabilistic numerics as being a bit more explicit about these assumptions, and actually then also incorporating uncertainty about whether your assumptions are true. The sort of, instead of just having an answer to the numerical algorithm that comes out and says this is done, having an answer with some sort of error bars. And Philipp's been taking a real sort of lead in this area from the machine learning side and using Gaussian processes a lot. And I just think it's a real exciting developing. It's not an area I've been active in as yet, but it's just a really interesting area for application of Gaussian processes. So it seemed really sensible to have Philipp come and give us an introduction to the area.
Thank you. Thanks a lot for this nice introduction. It's great to hear that Neil is saying he's not in the active in the area yet. I like it. This sounds great. It sounds like people are beginning to get interested. Before I start, really brief, some people asked me about how to do these animations for GP samples that I did in my last talk. There's a tech report I wrote for the machine learning sample school last year that you can find at tinyurl GP animate, which contains the MATLAB code and some maths on how to do this, and basically the entire script. With that though, let's get to the actual talk. So as Neil said, I'll talk about probabilistic numerics, and we'll have to talk a little bit about what I mean by that. My research group in Tübingen is called the Group for Elementary Intelligence, which is another word for the stuff I'll talk about. What do I mean by that? Well, first of all, I need to talk about what an intelligent system is, because that's sort of the name of our institute. This is my cartoon picture, and apologies to those of you who were here last year when I gave this talk. The first 5 slides will look eerily familiar. This is my cartoon picture of an intelligent system, an algorithm that interacts with the real world. The real world is over here, where the sort of nodes have been colored in this graph, and the algorithm, the machine, is over here. Here's how this machine interacts with the world, and I'm sure you will all recognize this kind of pattern. Everything starts with some data, which you collect in the real world. You use this data to build a model of the world that you're interacting with. That model involves variables and parameters, because this is the Gaussian process winter school. I can talk about variables and parameters, and you know what I mean. These are the things that we have a probability distribution over, which are the model of the world. These are the things that we fit to make this model a good model of the world. Once you have this model, you use it to predict how the world is going to change, how the future is going to look like for this world. In machine learning, we often don't do that. We assume that the world is static, and we just pretend that the future looks exactly like the past. But in the real world, things change as we interact with the world, so we need to predict changes in the world. And then, based on these predictions, which might have as a functional input some actions that the algorithm took itself, you can try and optimize those actions, which are things that happen again in the real world, such that the predicted future is somehow beneficial. Beneficial for something that we want the algorithm to do, or maybe if you think of an intelligent system, something that's beneficial for this intelligent system itself, because it's trying to survive or make the world a nicer place. Now, how do we actually do these individual steps? So, depending on what your background is, you have different names for these different parts of the algorithm. If you're a machine learning person, then you're interested in this bit up here, and you call this machine learning, or inference, or statistics. And then this bit is boring. It's just sort of a little bit of solving differential equations at the end. If you are an engineer, then this bit is boring. It's called system ID, and you just sort of do it on the side. And this bit is interesting. It's called control, and you care all about it. Obviously, I'm starkly simplifying here, right? How do we do this bit up here? Well, we all know how we do inference. There's basically 2 major steps. The first one is some kind of probabilistic computation using Bayes' theorem to construct a posterior distribution over these variables. And that involves, on a sort of elementary level, integration, marginalization, and conditioning. And we use all sorts of complicated algorithms to do this conditioning. For example, we build variational bounds, we do Laplace approximations, we use approximate inference schemes, we use MCMC as a quadrature method. Maybe you even use a classic quadrature rule, like an actual rule that constructs an integral in a numerical way. Or maybe you're lucky and your probabilistic model is a Gaussian process, then this here involves just inverting a matrix. It's an analytical linear operation. This bit up here is, now once you have the sort of this model, this probabilistic model of the world, you have some parameters that you'd like to choose optimally so that they sort of make this world, this model as good as possible. So for that you have to solve an optimization problem. In machine learning, we use up here all sorts of nice numerical optimization algorithms for continuous and discrete domains. We use global and local optimization methods like conjugate gradient and BFGS and various algorithms in that form. This is the inference part. Once we've done that, the prediction of the future in general involves solving some form of differential equation. Sometimes it's a very simple differential equation, sometimes it's a very hard one, sometimes they're ordinary, sometimes they're partial. I'm going to, in my talk, if I get to it, let's see how far I get in this talk about ordinary differential equations and how what we're currently doing to solve them. Basically, the classic idea for solving ODEs are Runge-Kutta methods, and I'm sure many of you have heard that name before. And then finally, this final step is sort of at the same time very straightforward because it's just again optimization essentially on a conceptual level, but it's also particularly challenging because it's folded in with the prediction of the future. And that's sometimes called control, and it's a particularly challenging kind of aspect actually. Okay, now as I said, we use these individual algorithms to do these computations. We use a variational bound, and we use BFGS to optimize the hyperparameters of our Gaussian process model. And when we write our papers, we write, oh, for this problem we used an off-the-shelf solver, an off-the-shelf optimizer, or we just constructed a variational bound. What that means is we're treating these individual, these are methods that are called numerical algorithms. We use these methods as black boxes that are just tools that are handed to us by some other community, and then we just assume that they do the right thing because they've been developed by some smart mathematicians. The downside of that is that each of these algorithms performs an approximate computation. Because usually what they're supposed to do, these methods, are intractable problems, right? We don't know how to solve an integral here, so we do it approximately. We don't know what the minimum is here, so we sort of just run an optimizer for a while and hope that it finds something good. Now, each of these algorithms causes a finite numerical error, and we often just sort of hope that error is small enough and that we don't have to worry about it that much. That means that often we have a situation where these individual algorithms cause very different kind of errors, and we don't necessarily notice how strong their effect is on the overall computation. So a cartoon picture you could have in your head, and I don't have an actual sort of concrete example for that, but I think it's sort of a realistic picture, is that you might run a variational bound here which is precise to roughly 10% relative error, and it takes 20% of your computation time, and then you run an optimizer which ends up being precise to 10 to the minus 7, but it took 30% of your computation time, and then you run an ODE solver which is super complicated, and it takes 50% of the remaining time, and it's 10 to the minus 16 precise, because it's a super precise algorithm that just works really well on this problem. Now that seems really wasteful, because the overall computational error might be completely dominated by this cheap bit up here, which you just couldn't make better. And this method here spends a lot of time trying to do something that isn't actually needed at all in the first place. But we don't know how to make it sort of less precise, such that it can deal with the fact that the previous computations were imprecise. So what we'd like to have are numerical algorithms for each of these steps, at least that's what I'd like to have, which can deal with all of these variables actually being random variables, being uncertain probabilistic variables. So I think it would be cool for machine learning if we had algorithms which can deal with all of their inputs being uncertain probabilistic variables. And then this thing here would actually be a proper factor graph. It would be an actual computation of this representation of this computation which involves functions which deal with uncertain inputs and which ideally also quantify their own uncertainty that they create by performing a finite precision computation. So I want these algorithms to be sort of probabilistic computations. Another way of talking about that would be to say, I want them to be learning algorithms. I want them to be inference or statistical algorithms. Now if you think about, at first this sounds a bit weird because these methods are a lot older than at least machine learning. Maybe they're even older than statistics in some cases. And you could wonder why you should think about them in terms of learning. But actually, if you think about what these methods do, they actually are, in some sense, learning algorithms. Because what is a numerical algorithm? Well, a numerical algorithm, at least for the purpose of this picture, is a method that estimates an intractable property of some function given evaluations of some function values that you can directly observe. So it's something that estimates something that you cannot directly see given something that you can directly see. And that's inference. So a quadrature method estimates the value of an integral over a function given evaluations of that function at various points. An optimization method estimates the root of some function, the gradient, given evaluations of that function at various points, at least for continuous optimization. For discrete optimization, you can think of a corresponding formulation. And an ODE solver, I don't really know what word for you to use for these methods. Are they analysis methods? Are they ODE solvers? I don't know. These methods that solve differential equations, they estimate the solution to this kind of structural equation given evaluations of that structural equation at various points. Now, from just phrasing this like this, you can hear that it's an inference problem, that it's sort of talking that I'm talking about a learning problem in some sense. And this is actually not a new observation. Do I have this somewhere? They're missing. There it is. There's some citation. So statisticians have actually noticed this long ago already, about 30 years ago. 20 odd years ago. Percy Diaconis wrote about it in 1988, Antonio Hagen in 1992. So this idea is not new. Percy Diaconis actually argues that Poincaré talked about it in 1896. I'm not sure to which degree this is actually true, but maybe there's actually something going on there. So this is actually an old observation, but it hasn't really caught on that much in statistics or in numerical mathematics. I think the reason for that is less that this is a bad idea and more that it just didn't fit into either of these two communities. Now, numerical mathematicians don't like this idea because it doesn't sound like maths. It sounds like statistics, and they don't really like statistics. They don't want to have statistics in their algorithms, maybe understandably, because it's such a mess. And statisticians, at least some of them, don't like this idea, and I sort of know this from actual papers and blog posts, mostly because this isn't actually a random problem. Normally in statistics, you think of trying to somehow remove randomness from a problem or deal with randomness in a setup. Now, these problems are not necessarily stochastic in nature. I mean, some of them are, but the basic problems here are not stochastic. If you integrate a function, there's only one function you're trying to integrate. There's no randomness about it. You can evaluate that function everywhere. It's just one thing you're looking for. And if you're looking for the root of a gradient, then there's only this one function, this gradient, that you're trying to find the root of. There's no randomness going on. So if you like to think of probability distributions in terms of randomness, then this doesn't really work. But if you think of probability in terms of uncertainty, then it does work. Because it's easy to write down, this is my favorite example, a function. This is a function I just wrote down on this board. It's this wide. It took me about 5 seconds to write it down. And it's deterministic. It's just this. So for those of you who can't read this, it's the exponential of minus sine squared of x minus x squared. So that's a function that you can evaluate on a computer for any value of x on the real line in, I don't know, a millisecond. And I could write it on a whiteboard in a very compact form. And it's a deterministic object. There's nothing random about it. But if I write an integral in front of it, dx, maybe even with limits, then I'm pretty sure no one in the room can tell me what that number is. This is also a number. But you don't know what that number is as a function of a and b. Why? Because it's not in any of the tables on integrals, at least those that I looked up in. So now, what is your answer going to be? Is it just, I don't know, I have no idea? Well, no, because you can make a plot of this function, you can look at it, it's a regular, it's a smooth function, it looks like a bumpy Gaussian, right? So you can think about what the value of that integral might be. You might be uncertain about it, maybe it's something like 2 pi, roughly, right? Square root of 2 pi, I don't know, with a little bit of corrections. So you're uncertain about the value of this thing, and you'd like to learn more about it. So if you think about probability distributions in terms of uncertainty, then it's not a problem to use uncertain descriptions on deterministic problems. That's sort of the main sort of sermon on this. Now here is our path through sort of numerical mathematics for the next almost an hour. The basic idea of how we're going to study these methods is it's very similar for all of these areas that I just sort of highlighted in this cartoon picture. And It's just the degree to which we understand these methods that varies a lot. What we'll do is we'll typically think about these inference problems in a formulation that uses Gaussian distributions, which is why I'm here, I guess. And the reason for that is the same reason that I argued for on Monday why we use GPs. And it's because they allow us to formulate nonlinear problems in terms of linear algebra. And linear algebra is the one thing we really know how to do well on a computer. Then we'll do probabilistic inference. And then obviously, because these methods are not high-level machine learning algorithms, but they are inner loop bits, sort of the tools we use to build machine learning algorithms, we have to really think about how complex they are, what their computational cost is. And we have to find methods that are actually fast and work well in a challenging setting. And usually that will involve using some kind of factorization structure to really keep track of which variables we have to combine with each other and which variables we can deal with separately. And the typical result then will be that we'll rediscover either exactly an old method that already exists, or at least something that is close to an existing method. Actually, of course, the real research program is the other way around. We start with these classic methods, try to understand how you would derive them in a Gaussian way. And then once you have this, okay, on the one hand, it's nice to have just a probabilistic understanding of an existing method, but it also usually immediately means that you can generalize the existing methods simply by doing all the things that we know how to do with what to do with Gaussians, just by adding noise, by going nonlinear, doing non-parametric formulations with Gaussian processes, and so on. So I have three case examples for these numerical problems. The first one is the one that is going to be the shortest one, partly because it's not actually my area of research. I'm going to be talking about some other people's work, and partly because it's, well, I don't know. Maybe it's just actually that reason. It's interesting as it is. It's also, from a Gaussian process perspective, maybe the most straightforward kind of connection, and that's integration, quadrature. So the problem I'm talking about here is, as I said before, trying to estimate an integral over a function from evaluations of that function, and you also have to choose where you put those evaluations. The idea is to use a GP, and actually that's the entire idea. Why? Because, so we've already mentioned this now several times over the past 2 days. Just to remind you again, Gaussian distributions are closed under linear projections or under affine operations. Now, most of the time so far, so this is this property that if you have a Gaussian distribution over some variable z, then you also have a Gaussian distribution over any linear map of z. In fact, this can even be used to define a multivariate Gaussian distribution, as we heard. Now, usually we think of these linear maps as just matrices, but you can also think of this as a Gaussian process, an infinite dimensional object with a linear operator acting on this infinite dimensional object. And one such linear operator would be integration. Integration is obviously a linear operation because the integral over the sum of functions is the sum of the integrals over those functions. And that means that if you have a Gaussian process belief over a function, that implies that you also have a Gaussian process belief over the integral over a function. So here's one of my plots again. This is, unfortunately, again, a square exponential Gaussian process. By the way, I don't actually worry so much about the square exponential. I worry about the d, because it's not a squared exponential. It's just a square which has been exponentiated. But, so this is a square exponential Gaussian process. And I have here 3 yellow regions, which are regions over which I would like to compute an integral. So I would like to know the integral over this function from here to here, from here to here, and from here to here. Now, because this is a Gaussian process, this belief over the function values and the integrals jointly is itself a Gaussian process. It just has 3 more dimensions than the belief over this function. So this, and this one. And they co-vary with each other. You see that the expected value for all 3 of these integrals is 0, and the variance has varying width because this is a larger integral than this, so we're expecting more variance. And maybe you can see 3 yellow dots moving up and down here in a sort of coordinated joint fashion. That's because these 3 variables have a joint distribution over each other. Now, if somebody told you what the function values of this green function were at various points, here's my blue linear data set again, then you can use those directly to compute your belief over the integral over that function. So now my belief over those integrals has changed. This one has moved down. We're expecting this to be a negative value, this integral. This is about 0. This is a positive number. And we've become more certain about where they are. That's the basic idea of how you could construct an integration or a quadrature rule from a Gaussian process prior. So you want to know what the integral over a function is, you choose a particular Gaussian process prior, and then you evaluate this function at various points. That gives you a Gaussian process posterior over what the value of the integral is with uncertainty, and then you hope that this uncertainty is well calibrated and actually represents something meaningful. Now, you could ask, where do I have to put those points? Because that's sort of half the idea of a quadrature rule. And you come up with various rules for how to choose where you put those evaluation points. A simple rule, and it's maybe the most widely used one, is to say, I would like to have evaluations such that the posterior uncertainty, posterior variance over the value of the integral drops as quickly as possible. And now I could try to optimize the location of the points where I evaluate as a function of the posterior variance over this integral. Now if you do this for, not actually this prior, but for the, I think I did this for a rational quadratic, but like, don't quote me on this. Here's the kind of picture you get. So I have done for number of evaluation points from 1 to 10, did this optimization, asked where should I put the points such that the posterior uncertainty is minimal. And it's clear that, well, actually, it's sort of not, maybe not so clear, but for the stationary process, it's relatively intuitive that if you only have one evaluation, then you want to evaluate in the middle of the box that you want to integrate over. If you have two evaluations, you want to sort of not actually be at 0.25 and 0.75, but sort of 0.28 and 0.72, something like this. And then these, obviously these sort of points form a nice kind of pattern. If you had a different prior over the function, this pattern might look very different. So if you have a non-stationary belief over the function values, these points might be non-uniformly distributed. This is an area often called Bayesian quadrature. It was maybe started again by Tony O'Hagan, whose name we've now heard very often. There is also some interesting work by Tom Minka in 2000, and then now there's sort of a small community here. A key player in which is Mike Osborne, who's not here this year, but he was here half a year ago, talking about basically this area. The tricky bit here is, as you can sort of tell, this is from a Gaussian process perspective, this is actually relatively straightforward. It's just all analytical. The interesting bit comes in if you have knowledge about the function that is sort of not quite commensurate with the Gaussian process formulation. So if you know that your function only takes positive values, for example, then this becomes more tricky because it's hard to encode that in the Gaussian process. And this is what this community, I think, is mostly tackling. Sort of trying to build quadrature methods that work well on sort of more structured quadrature problems. Any questions on this area? Mm-hmm. Yes, Alessandra.
If you change the kernel, the configuration of the points will change.
Yes. And you can think of all sorts of interesting kernels that would give an interesting distribution. If you think about the Wiener process, for example, I'm sure you'd get sort of, at 0, you don't need to put any points because you know the function is 0, and you need more points over here because that's where you're most uncertain, something like this. Okay, so that was quadrature. Let's go to the next step. This is going to be the main part of the talk, optimization. So I already talked about this last year when I was here. This time I'll have to spend a little bit more time on it, and then we'll see how far we get with ODEs. So I'll talk about two kinds of optimization problems which are closely related to each other. One is the nonlinear version of the other one. When I talk about linear optimization, I mean maybe the most boring problem you can think of, and that's inverting a matrix. So I would like to solve this kind of problem. There is a matrix B, which I'll usually assume to be symmetric and positive definite, because that's sort of an interesting setup, because it generalizes nicely to nonlinear problems. And there's a vector B. This might be a large quadratic matrix, and this is a large, long vector. And I would like to know what x is. Maybe more generally, I'll have lots of b's here, and I want to know lots of x's. And those b's maybe come from a distribution. I would like to know what the distribution over the x's is. Basically, I want to know what the inverse of this b is, or what the pseudo-inverse of this b is. The nonlinear version of that is maybe the one that you're most familiar with, and that's, I haven't actually written this down. That's the problem of optimizing a quadratic function which is of the form 1/2 x transpose bx plus, no, minus b transpose x. So the gradient, no, okay, so this is, sorry, correction. This is the function you're trying to minimize when you're solving this linear problem. More generally, if you had a general function f of x, which is not a quadratic function, but maybe convex, or maybe not convex, then one way you could try to optimize a general function is to approximate it in this kind of form. To write it as a constant at some location xt. I actually have a slide for that. Good. So I'll show that in a second. Sorry. And what you'll end up doing is Newton's method, which involves doing steps like this. I don't know why I put this here, not on the next slide. Sorry about that. And it involves finding the inverse of the Hessian of an objective function everywhere. So that's a little bit like this problem, because you have to find essentially the inverse of a matrix. But that matrix is not just one matrix anymore, it's a function changing everywhere. Here is the formulation for the nonlinear problem. This is the motivating slide. And I put it in the front, even though it's the nonlinear case already, because this is how we began thinking about these problems sort of just over a year ago. And I think it's sort of a good as a sort of a motivational slide to understand why it's interesting to think about these probabilistic numerical formulations. So here is the nonlinear optimization problem. Sorry for the confusion. I'm talking about some general function which is a real-valued function mapping from a real vector space with n dimensions to the real line. We're interested in finding the local minimum of this function, so that's a root of the gradient with associated positive definite Hessian. An example of that would be finding good hyperparameters for a Gaussian process regression method. Right? You'd like to find the minimum of some log marginal likelihood function, for example, which is a nonlinear function. It's not even necessarily convex. The typical algorithms we use for that, minimize or fmin or minfunc, are functions that start at some initial value x0 and then iterate through xt's to hopefully converge, hopefully quickly, to a good root of the gradient. And the sort of classic high school way of doing that is Newton's method. So we approximate locally the true function we're trying to minimize to second order. So at location xt, we can write, assuming this is actually a convergent Taylor series, or at least these objects exist, we can write f of x as a constant term plus a linear term involving the gradient of the function plus a quadratic term involving the Hessian of the function, and that Hessian I'll call b, partly to make the connection to linear problems and partly because in the literature this thing is often called b. And that's a function taking in an n-dimensional vector, returning an n by n square matrix. Now this quadratic approximation does have a local minimum if b is positive semi-definite, or positive definite, sorry. And that minimum is at a new location xt plus 1, which is the old location xt minus the inverse of the Hessian times the gradient of f. And that's sort of this is the multivariate version of a classic algorithm you've probably learned in high school, Newton's method for finding roots. Okay, now the problem with this setup is that you have to find the inverse of this Hessian. And if n is a large number, as it might be if you're optimizing a neural network, then inverting that matrix is cubically expensive in n, in that large number, and it might be too expensive to actually perform. It also sounds really wasteful because we'll just do it again in the next step. Right? We'll now take a step for this algorithm, and then we get a new Hessian, we have to invert that Hessian again. Now if we do a small step, the new Hessian will look a little bit like the old Hessian. And it sounds really wasteful to just start from scratch and recompute the inverse of a matrix. You'd like to have a method that sort of drags around the fact that the previous Hessians were a little bit like the new Hessian, and sort of use that to find a faster approximate inverse to this Hessian. These methods actually exist, and they're called Quasi-Newton methods. And I'm sure all of you have used them already, maybe without knowing. The most famous one is the BFGS rule. Hands up, who has heard of BFGS before? A little bit more, over half the room, so that's good. Who has used an optimizer consciously before? Is anyone who's called minimize or fmin or minfunc or optimize or something? It's about the same number of people.
You should have all done it.
Yeah, you've probably all done it already in the practicals.
BFGS is cool at one point, but you may not have noticed.
Okay, so you've probably already used these methods. There are more of them in this family. They're also called DFP for David and Fletcher Powell. This was Boyd and Fletcher, Goldfarb, Shano. There's something called the symmetric rank 1 rule, and there's something called the Powell symmetric Boyden method. There are more. I'll talk about some of them later on. They are all sort of related to each other, and they all do the same thing on some elementary level. They iteratively built an estimate for the Hessian of the objective function and equivalently for the inverse of the Hessian function. And they do that by iteratively updating this estimate that they currently have at time t to a new estimate at time t plus 1 by adding two low rank terms, typically two rank 1 terms, so that the entire update is rank 2. Why? Because that means you can compute the inverse of the Hessian very, very efficiently. Now, how do they come up with this, with these two vectors u and v? Well, they make two requirements, and this is sort of classic derivations from the 60s and 70s and maybe even the late 50s. They say, well, I want this estimate of the Hessian to fulfill some kind of functional relationship that I sort of know should hold for Hessians, or at least approximately hold for Hessians. And that requirement is that the difference between two consecutive gradients, evaluated at two consecutive locations, should be roughly equal to the Hessian that I'm going to estimate, the approximate matrix, times the distance between those 2 points. So that's like a difference, that is a difference equation actually. It's like a finite difference derivative, if you like. So if you divide it by, you can't divide by this because these are vectors, but if you sort of mentally divide these things over here, you can see that this is sort of a finite difference relationship. So that's a functional requirement that says, I want this Hessian to fulfill a second relation, so a linearization of the Hessian along those two vectors. This vector is often called y, the difference in observed gradients. That's an observation that the method makes, essentially. You ask the function, what is your gradient, and you get back an observation. That difference between locations, that's a choice that the method makes, essentially. It's an action taken, and that's often called the vector S. So then we can write this simple equation in this sort of simple compact form. Now, there are n squared numbers in this matrix, and there are n numbers in this vector. So that's not enough to define what our new estimate should be. We need a regularizer. And those of you who know about the connections between statistics and probabilistic inference already can sort of get an idea of what's going on. That regularizer will say, well, I want an estimate that has this property, but I also want, apart from that, I just want as little as possible to change. Like everything should be as good as before, but only this should also hold now. So to make that more precise, you have to say, I want the change in the Hessian to be minimal under some norm. And you have to choose that norm. By choosing that norm, you're going to choose which algorithm you're going to use, and we'll see to what kind of assumptions it amounts. The norm that these methods choose are called Frobenius norms. Many of you may have heard of Frobenius norms for matrices. It's essentially a least squares norm on the elements of the matrix. You can write this sort of these two requirements, minimal norm under this requirement, as a sum of two losses. One sort of perfect loss that has infinite value if you're arbitrarily far away from the correct answer. This is the yellow bit, that's the functional requirement, and the standard Frobenius norm. Now if you minimize this, it's a sum of two quadratic norms, so you can minimize this in closed form on a piece of paper. That tells you what your new estimate for the Hessian should be, and that's the method that you implement. That's the rule that these algorithms implement. And that's sort of one of special cases down here. This is called Boyden's method. This is a famous, very old method that's not used today anymore. This Frobenius norm has a weight in general. You can define it generally with any weight. And by choosing the weight, you get different forms of algorithms, including BFGS and DFP and all the other methods. Now, if you have some statistical training, then you can probably guess what's going to happen next. The observation you made is, oh, okay, you're minimizing a regularized loss. We know how to interpret that in a probabilistic way. Minimizing a regularized loss is the same as maximizing minus that loss. That's that first line up here. Maximizing, these two numbers are, they are both negative, and you can interpret them as the logarithm of a probability distribution, which is then sort of a number larger than, between 0 and 1. You have to check that it's a probability distribution over something meaningful. This one is not a probability distribution over B. It's a probability distribution over Y given B, also known as a log likelihood. And this one is actually a probability distribution over B. It's called a prior. Maximizing the sum of those two log probabilities is the same as maximizing the exponential of this term, because the exponential is a monotonic function. So it's the same as maximizing the product of prior and likelihood. And the product of prior and likelihood up to normalization is the posterior. So this is a maxima posteriori estimate, if you like, just by rephrasing the derivation of these methods. It's the exact same derivation, just with different words, but the same numbers in them. Now, we need to check what kind of probability distributions those are. Well, it turns out, so Frobenius norms are quadratic norms, and the other functional requirement I wrote as a quadratic norm as well. So the exponential of a quadratic, that's a Gaussian. And that's why I'm here and not in the Laplace process workshop next door. There.
If you go back just one slide, where's the limit coming from there?
This one, oh, it's because I want this to be strict. I want y to be equal to bs. And there is infinite penalty if you're ever so slightly away from it. We'll relax this at some point and talk about what you can do with relaxations.
Is V the weighting?
V is the weighting, yeah, of the Frobenius norm. So those two prior and likelihood, you now identified both as Gaussian distributions, and they both contain some covariance term which corresponds to the weight in the Frobenius norm, and that it will turn out to be the prior covariance of the prior, and it also determines the posterior covariance of this posterior. Now, this posterior covariance does not feature in the derivations of these classic methods, but it's there. It's just, you can just compute it if you want to. It's just not necessarily actually part of the derivation. In fact, at least it's there in this general formulation. We'll notice that in 5 minutes that there are some cases where it's very hard to think about what it actually is. Okay. So we did this kind of formulation. This is something that I did with Martin Kiefel just over 2 years ago. We noticed that this is classic derivation. This is just something we looked up in a paper that existed from the 70s. And not this slide, but this slide. And we noticed, okay, that means we can actually interpret these methods as Gaussian inference, as they are. We can just read what they do and try to understand exactly what they do. Now, for the past year or so, we've just been spending time trying to understand better what exactly they do. Because it turns out, if you look really closely, there are really smart choices going on in these methods. And that's actually a recurring theme. So as we go through trying to understand numerical methods from a probabilistic perspective, it often happens that the initial connection is relatively straightforward. But then when you want to build a really good method, you discover that these old people who did this in the 70s and 50s and sometimes in 1900 were actually really smart. And they did some very smart things that are not so trivial to reconstruct. And you have to really work hard to understand why they did this. And often they did it not because of probabilistic arguments, of course, because they didn't think probabilistically, but they still ended up doing something quite smart, even from a probabilistic perspective. And I'm now going to try to recreate that kind of thought process, but from sort of de novo, from scratch. So instead of trying to follow up this derivation even further, I'll sort of pretend that nobody has ever told you about BFGS. You don't know anything about linear optimization. Let me tell you how to construct one if you were sort of an unspoiled Gaussian inference person who I can just tell something new to. And then we'll see what the connection is later on. So that's exactly what I'm going to do. So I just set this. I'll move back to linear problems first, actually, because they are really interesting in themselves already. So how many of you know how to invert a matrix? If you raised your hand, does that mean you know how to write a backslash operator in MATLAB? Or does it mean you really know how to implement a matrix inversion algorithm? What kind of matrix inversion algorithms do you know? Shout something out. So pivoting is sort of a trick that happens within Gauss-Jordan elimination, basically, yeah? So Gauss-Jordan elimination is one of them. There's maybe one famous other one, which is interesting because it's sort of... So Gauss-Jordan is a method that people use if they actually want to just the inverse of the matrix and they can wait for the algorithm to end. What do you do if B is too large to invert it in closed form? Conjugate gradient, yes. So we have to think about conjugate gradient. Conjugate gradient is an algorithm which iteratively solves. So it repeatedly it has estimates for x, iteratively updates those estimates for x. If this is an n by n matrix, it does m steps where m is much less than n typically, and then hopes that you're close to the true solution. Who of you has used this method before? Okay, a few. If you run this for 10 steps on a 10,000 by 10,000 matrix, how good is the estimate afterwards? You would like to know, no? You'd like to have an error estimate on how wrong that estimate is. Actually, it's relatively easy to estimate the error on x because there's a residual that you get out. But you also get an estimate for the inverse of b. And getting an error estimate on that is a lot harder. And I'll try to give you a feeling for how we would get an error bar on that. That's what a probabilistic numerical method should be able to do. And as far as I understand, they are not out there yet. Okay, so if we know that B is a positive definite symmetric matrix, we know that we can write all positive definite matrices as R times R transpose with some general matrix. If it's positive definite, then sort of R has to have a certain size, but we can all write them in this kind of form. Now, if we didn't know anything about BFGS and just wanted to build a probabilistic method that does inference on these kind of problems, you might want to say, okay, maybe I just build a prior on R, and then I do inference on R. What would be a good prior on R? I already have it down here actually. Sort of the classic prior that people use for positive definite matrices is the Wishart prior. And if you've sampled prior covariances for a Gaussian matrix at some point, you might have come across the Wishart distribution. The annoying thing with the Wishart is that you can't do this kind of inference where you get to observe linear projections of the matrix, at least not in closed form. It doesn't have the right algebra. You need something that gives you linear algebra in inference. And the one tool for that are Gaussian distributions. So we're going to build a Gaussian estimate even though Gaussians don't really have the right geometry for the space we're looking for. The space is the space of positive definite matrices, and that's a cone. It's hard to build a Gaussian over that, so we'll do a sort of a moment matching. Here's a picture of how to get the moment matching for this kind of problem. We'll say that the matrix B we're looking for is a symmetric quadratic matrix, and it can be written as R times R transpose, where this is essentially a draw from a Wishart. A draw from a Wishart is you repeatedly draw the columns of R independent of each other. And so each column is drawn from a multivariate Gaussian which has n dimensions and has a covariance of essentially V divided by a scalar constant, which is the degrees of freedom of the Wishart. We draw that many of them independently after each other, and then take the outer product of that matrix with itself. That gives you a symmetric matrix which, assuming that mu is large enough, is positive definite with probability 1. Now, Wishart distributions are annoying, so we're going to use Gaussians. We're going to do moment matching on this. The covariance of this matrix that comes out of this process has a particular form. So the covariance between the ijth element of that matrix and the klth element of that matrix, that is a particular object which took me some time to understand, and it's called the symmetric Kronecker product. It's almost like a Kronecker product, but it doesn't have all the nice properties of the Kronecker product. It sort of has a few really annoying properties that make a lot of the analysis very complicated. And it took me a long time to get to that point. Last year when I was here and I gave this talk, I was still talking about Kronecker products, which makes things less elegant in the following derivations. With this kind of formulation, things are a lot nicer. Why? Because if you have that kind of matrix, that's now our prior for B, and you multiply that B with another matrix, S, which might be a vector or a slightly broader matrix, then you get out some vector Y. That's exactly what we're trying to do inference with. And you can now write down, because this is a linear map, so this is a linear map of B. This is an observation of this linear map. Gaussians are closed under linear maps. So you can just write down what the posterior looks like. It's a bit tedious. It took me a few weeks with this silly symmetric Kronecker product. But it turns out it works. And the posterior is another Gaussian over the elements of B, which has a really complicated mean and a really complicated posterior covariance. Now that expression is not going to be too helpful for you if you just sort of stare at it. But if you've seen a lot of Quasi-Newton methods before, update rules like BFGS and DFP, then it'll look very familiar to you. That's actually the general form of Quasi-Newton updates. It's sometimes called the Dennis class of updates, because a guy called Dennis wrote a paper about them in 70-something. Actually, that's not the Dennis class. It's only the Dennis class if you assume you have just rank 1 observations. If you do individual updates, just B times a vector. If you have several, more than 1 observations, then the posterior gets slightly more complicated. The posterior involves inverting small sort of Schur complement matrices of size m by m, where m is the width of this thing. But if we just talk about one step first, then we can actually identify a lot of existing methods. So by choosing the prior covariance in a particular way, we get lots of interesting existing methods. If you choose the prior covariance to be 1, the unit matrix, then we get an old method out that's called Powell symmetric Broyden update. If we choose the covariance in a sort of slightly weird empirical Bayes way, where after each step you use as the covariance the mean from the previous step, you can think about whether that's a good idea or not, something comes out that's called the Greenstadt update. And if you choose as the prior covariance the matrix itself, which sounds really weird, but let's assume we could do that, then you get something out that's called David and Fletcher-Powell method. And if you interpolate between those two updates in some sense, by adding them together with a bit of a scaling in between, you get the Broyden-Fletcher-Goldfarb-Shannon update, BFGS. Now, you can ask, how does this work? How can I choose a prior covariance that is equal to the matrix I'm trying to infer? That sounds really wrong, right? But it turns out that you can actually do this if you only care about the mean. Why? Because this mean update only involves projections of the prior covariance. It's actually similar to the like the plot I had on Monday, sort of the argument for Gaussian processes. You observe that to compute the posterior mean, you only need projections of the covariance. And this projection is of the form prior covariance times S. And you know what B times S is, you just observed it. So you can just plug it in. Why would you do that? Because it gives you a method, and I don't have time to go through this in detail, that is sort of naturally scaled. It means that if you have a very large B, then your prior covariance is very large, and your error bars are large. And if you have a very small B, then your prior covariance is very small, and you get very small error bars. So you get a method that's sort of scale-free, if you like. And that's actually an argument that people made in the 80s when they derived these methods. They said this is sort of a naturally scaled formulation of this algorithm. But there's actually, and this is only something we can realize now that we have the probabilistic formulation, that is particularly interesting about these methods. And that is, if you wanted to do several steps, more than just this rank 1 update, but sort of a rank m update, then if you want to do this in general, for a general covariance matrix, we would have to construct this posterior mean, invert these m by m matrices which are in here. I should have made them in red. Actually, I have a slide for that here. So this is what the posterior mean looks like. And you would have to invert these matrices, which are projections of the line searches on the covariance. So this is tedious. It makes the algorithm expensive. And I said the big problem in building a good numerical algorithm is to find a method that is very fast. Now, you could say, well, maybe I can make this sort of a fast algorithm by making sure that this matrix is diagonal. Because if it's diagonal, then I know how to do the inverse in a very fast way. It actually turns out that if this method if this matrix is diagonal, and what that means is that these search directions have to be conjugate under the prior covariance, then if this matrix is diagonal, then actually this rank m update can be written as a sum of rank 2 updates. And it turns out that if this is true, if this matrix is actually diagonal, then what the classic methods do, which is just to iteratively update the mean, is actually the exactly correct thing to do. It's the exact correct Gaussian posterior mean of this method. So now we know that some of these methods are actually correct, and some of them are not quite correct. So it turns out that this one is not correct, because for this particular choice of prior covariance, this matrix is not diagonal, so you're not even allowed to do what they do. But for those three, it turns out, and this is sort of a little lemma or theorem, those three actually have diagonal covariance matrices. They have conjugate search directions under the prior covariance. Yeah. Now, the word conjugate rings a bell. And the other step is, we just observed that for DFP and BFGS, the prior covariance is actually the matrix itself, in a sense. So we have here we've found a method which chooses search directions which are conjugate to its prior covariance, and that prior covariance is the matrix itself. So that means the search directions are actually conjugate directions under the matrix we're trying to invert. So that sounds like an algorithm we know. It's the conjugate gradient algorithm, and actually, so I've stepped forwards. There's a theorem that says BFGS and the conjugate gradient algorithm are actually the same algorithm when applied to a linear problem. So one way of coming up with the conjugate gradient algorithm, if you wanted to, in a really sort of convoluted backward thought process, is to start with a Gaussian prior on the elements of a matrix, and then choose a very particular prior covariance matrix, apply it to this linear problem, and out comes the conjugate gradient algorithm. That's not the nonlinear conjugate gradient algorithm, but it's the standard conjugate gradient algorithm. That's the fast matrix inversion algorithm that we all use when we have to invert matrices iteratively. What happens if you do that, and so this is where we start to think probabilistically, as sort of an interesting structure. So every time you multiply this matrix, B, that you're trying to invert, with a particular vector S, which is a search direction, you get an observation of length n, y. So that's n numbers that tell you something about the structure of the elements of B. Now if you have n square of those numbers, and if they happen to be linearly independent, then you know everything about B, and you're done. So after you've done m steps of this sort of rank m of these n long observations, there should be some space in which you are certain about certain parts of the matrix. And you can actually parameterize that space using the singular value decomposition of the line searches. I'm not going to go into detail. This is a little bit tedious. But the point is, there are sort of certain parts of B that we know perfectly after we've made a certain number of observations. And there are certain parts of B that we don't know at all because they lie in a space that hasn't been spanned yet by the line searches. And because we choose B as our prior covariance, essentially, in BFGS and conjugate gradient, that means that after M line searches, there are certain parts of the prior covariance that we've now just been told by the algorithm. We basically sort of, now that we've done it, we can ask the algorithm, well, what was your prior covariance? And it can say, well, in a certain subspace, I can tell you what it had to be because otherwise it wouldn't have worked. And that's your natural prior covariance. That's a well-calibrated prior covariance that would work well. But there are certain other parts of the prior covariance that I can't tell you yet because I haven't actually used them yet. I didn't need to look at them yet. Right? But our first problem is that we need to be able to actually say which parts of the prior covariance are the ones that we know and which are the parts that we don't know. And we'd like to do that in a way that doesn't cost us anything because we want to have a fast algorithm. So what I'm looking for is a method that does conjugate gradient for how many steps you want it to do, and then tells you afterwards, oh, essentially I've been using a particular prior covariance matrix. To a certain degree I can already tell you what it is, and in that dimension I'm actually done. My posterior covariance is 0, but there are some parts left that I haven't seen yet at all. And to give you an error estimate, you have to guess what that part should be so that it sort of will work in the future as well. And on that bit we have to use some regularity assumptions, essentially do regression, to get a meaningful estimate for the uncertainty. There's too many clickers here. And another, so this is the final technical point. After that, I'll become a little more chatty again. An advantage of the great value of observing that we're essentially doing conjugate gradient here is that we know a lot of things about conjugate gradient. Among them, we know that conjugate gradient produces gradient directions which are orthogonal to each other. So because they are orthogonal to each other, they actually give us a basis of the space that has already been spanned by the line searches, because the line searches happen to be the same, happen to span a space that is identical to the space spanned by the gradients. So this is all sort of annoying linear algebra that you can find in textbooks. But it means that we know how to parameterize the space in which we know stuff, and we know how to parameterize the space in which we don't know anything, without any additional costs. We can use terms that we had to compute for the conjugate gradient algorithm in the first place. So what's left is to estimate the remaining structure of the prior covariance that we haven't yet seen to get a meaningful error estimate. And that's where it gets very hand-wavy and where we're sort of currently on a research level. Basically the idea is there are now some parts left of the prior covariance that we don't know yet. So some scales of B that we haven't seen yet. And the only thing you can do, as always in statistics, is to say that the bits that you haven't seen yet somehow have something to do with the bits that you've already seen. Right? And say they'll probably have a similar structure. Now because we are actively searching, trying to invert B, that structure is not necessarily IID. It might be something complicated, and actually there is theory about what that space looks like. It's the space of expanding Krylov subspaces. But nevertheless, there's typically some regularity. So here are 3 examples. Here's a particular term which you don't need to understand. There's one scalar term which gets lugged around in the conjugate gradient algorithm all the time. This is the sort of the elements of the diagonal of this diagonal covariance matrix or Gram matrix. For 3 different kind of matrices. So here I've inverted 3 different matrices using the conjugate gradient algorithm, and they have different eigenvalue spectra. And you see that for these different sort of classes of matrices, this is a matrix with uniformly distributed eigenvalues, this is a matrix with exponentially distributed eigenvalues, and this is a matrix with a structured eigenvalue spectrum, which has a few large eigenvalues in B, so small eigenvalues in the inverse of B, and then a few very large ones. And now you could guess that if you know if you have this kind of, so if you've seen this kind of picture, then you could guess that after I've seen this much of these numbers, I could guess that the next ones probably look the same. And after I've seen this many of these numbers, I could probably linearly extrapolate and say this is how it's going to continue. And after I've seen this many, well, I've got a problem. But if I know that there are only 25 of these small eigenvalues, and then the other ones have to be larger, I could probably build a method that sort of tells me I'm not converged yet, I'm converged already. Something like this. So what we'll need to build good probabilistic linear solvers is slightly more structural assumptions about the matrix, but then you can run conjugate gradient and without additional cost build a posterior error estimate over the elements of the matrix that you're trying to, or over the inverse of the matrix you're looking for. Here's what this looks like. So we're trying to find the inverse of some matrix B. We're doing this with one particular sort of little b. You might wonder about whether it might possibly work better with several b's, but let's say we only have one b. Then as conjugate gradient runs, I've done this for 10 different initializations, 10 different matrices B and 10 different little b's. This is sort of typically what conjugate gradient looks like on the gradient. So then the norm of the gradient drops very quickly because the algorithm converges. And while it does that, you can construct an estimate for the inverse of the matrix, which also sort of slowly converges. Now these red lines in the middle, these are the individual errors on the individual terms of, like, in that matrix. I've only taken 10 of them because if I would plot all 10,000, it would be a bit dense. This is something you could get from a classic conjugate gradient algorithm. What you couldn't get are those black error bars around them, which you can now construct. And the cost of constructing these error bars is almost zero. You get them essentially for free just by understanding probabilistically how this method actually does inference. Something you could then do with that is to say, okay, I've just tried to invert this matrix B, and now I did this with this particular B, and I found this particular X. Now I have some other B's that I also want to plug in here. And I don't want you to rerun this algorithm. I just want to use what you currently have as your inverse of the matrix. What is like I'm going to get new estimates for sort of what the solution of this linear problem should be, but I don't know yet how wrong they are, right? Because I've only constructed this inverse in a particular way to fit this particular X. How much do I actually know about the structure of this matrix? Now, you can actually do that, of course, just naively, and out comes sort of some errors for these elements of this X test. You could wonder how wrong they are. If you use this posterior Gaussian uncertainty over the elements of this B, because this is a linear map of these things, you can construct the posterior uncertainty on X test. And this is what these black lines give you here. By the way, you can see that these don't look particularly impressive. This is a relatively ugly kind of thing that's going on. And that's mostly because we don't understand yet well enough what the structure of these things are and how we can sort of build good estimation methods for this remaining posterior uncertainty. But at least they are well calibrated. They are large enough. Like what I sort of can't tell you because if I could show you some old plots of how we tried this initially, you would find lots of examples where the black lines are sort of this wide. So at least now we have methods that are reasonably well calibrated. Okay, so this was quite technical, and I apologize. It's just that's the most recent development. It's also the mathematically most rigorous one, I would say, at the moment. We're beginning to understand linear matrix inversion algorithms from a probabilistic perspective. I find this super exciting, even though it's sort of technical. I have to talk about conjugate gradient and orthogonal directions, because these methods are so elementary. They are really at the inner heart of the computations we do. And we're beginning to understand them as inference algorithms themselves, so I find this really cool. The interpretation is existing classic Quasi-Newton methods can be interpreted as parametric Gaussian regression applied to linear and nonlinear problems. If you only think about linear problems, then you begin to understand why you would choose these methods or build these methods in a particular way. Because they allow you to get cheap inference algorithms, because there's certain things are diagonal and cancel out. They're also well calibrated. They give you error estimates that have sort of roughly the right size. And in the case of BFGS, there's a particularly nice property that it's connected to the conjugate gradient algorithm. They're essentially the same algorithms in the linear case. And that means you sort of, for free, get a basis, an orthonormal basis, the gradients, of things in which you can describe the problem. So that gives you a neat way of constructing a posterior uncertainty without additional cost. The remaining posterior uncertainty over the elements of the inverse are sort of, then these are now numbers that you in a hard way have not observed yet. So it's like extrapolation. And of course, what you do to construct a posterior estimate is extrapolation. You look at the things you've already seen, you say the future is going to look similar to the past in some sense, and then predict what your uncertainty should be. there are also really, really many questions left. You sort of notice how I'm waving my hand about because this is all really new stuff. This paper hasn't even been published yet. It will go out next week on the archive. But for example, we have very few models for the structure of these matrices, and we're only beginning to understand how to choose estimation methods for the remaining parts of the matrices that we haven't seen yet. There's also an interesting property that conjugate gradient is not necessarily a it's sort of not necessarily a numerically stable algorithm. It has all sorts of flaws if you just implement it in a naive way. An interesting question you could have is whether we could use this probabilistic understanding, which gives you a slightly larger matrix to monitor, to get a better feeling for how well this algorithm actually converges. But I'm getting ahead of myself. Okay, very short. Yes, Neil.
I guess you can tell why sort of statisticians
Don't like this.
classical, because what you had that really nice plot at the beginning where you sort of said, oh well, you're right at the beginning, so you don't have to go back. Where you said, well, you've got these two approaches, quadrature or optimization.
Oh yes, yeah.
And now what you're telling them, I guess at the end is, and the result of your optimization is a distribution. In effect, that was what your last thing was saying.
Yeah.
But now the uncertainty in the parameters is coming from the algorithm you've used to do your optimization or the optimization, instead of uncertainty in your parameters from your modeling side.
No, so I'm also the uncertainty in the parameters also comes from essentially uncertainty over this structure.
The structure of yes, but that's sort of really in relation to the true structure versus the assumption about the structure that you made in the optimization algorithm. So then I guess a follow-up question is, how do you use this uncertainty in inference? So I wanted to optimize and come up with a point estimate.
Yeah.
But now I've got a distribution. I know what I need to do with the distribution if I intended to integrate, but now I've got a distribution, and can I do anything with that uncertainty?
So okay, so two short answers. The first one is this is I think a particularly interesting case because it's sort of an elementary version of the problem we have in Gaussian process regression. So when you try to optimize the hyperparameters of your Gaussian process model, you only, as we talked about on Monday, there's this infinitely large space of models for functions, and after finitely many data points, you can only identify the hyperparameters to a certain degree, and you can't identify the actual generative process of the function ever because it's infinite dimensional, and you need arbitrarily many data points. So if you had an uncountably large number of function values everywhere, and of those functions that were generated from this Gaussian process infinitely many, maybe you could actually perfectly identify, I don't know, what the Gaussian process was that generated this thing. And then you wouldn't have posterior uncertainty anymore in any way, because you'd have sort of fully identified it. Here, for matrices that we're trying to invert, things are much easier in some sense, because there are really finitely many numbers. So there are really n squared numbers in this matrix, in this inverse of this matrix, assuming it exists. And after you've seen all n squared numbers, you're not uncertain anymore. It's zero uncertainty. And now, of course, what you would like to have is a method that, before it has n squared numbers, in a meaningful way collapses. Now, what these methods basically tell you is, here is how you should have chosen certain parts of your prior parameter space, such that this would have worked really well, and such that it would have been sort of natural under some sense. But the remaining ones you don't know yet. So it's a very clear-cut sort of bisection between the things you do not know yet and the things you do know. And it's sort of a very clear case where you don't know, this is the one structure that I'm trying to predict, and this is the stuff I already exactly know. While in GPs it's sort of a little bit more complicated because there are infinitely many numbers. So from an inference perspective, I think it's a particularly interesting, maybe toy model, because it's so finite. What do I do with the uncertainty after I'm done? It's a Gaussian uncertainty over the elements of a matrix. And I'm going to do linear algebra with it. So basically everything I'll ever get to see are linear projections of these numbers that I'm Gaussian uncertain over. So that will always give you a Gaussian uncertainty, I would say. So the posterior, that uncertainty is actually a meaningful thing. And there's lots of questions that we haven't addressed yet. So, okay, I haven't done this at all, but here's a neat idea. I can't promise that it works because I haven't done it yet. But you could say maybe, and I wanted to have this plot, but I didn't do it because I didn't have time for it. Let's say I have a huge design matrix that I want to do regression with millions of data points. And I need to invert that thing. I need to invert an inner product of the design matrix with itself to do linear regression or something. Now, conjugate gradient would mean I have to go through this entire thing, sort of multiply with various vectors to have converging residuals. Now, an alternative thing you could do is you could say, well, I'm not going to actually multiply, because this matrix is so large, I'm not actually going to multiply this vector with this matrix because it costs n squared and I can't do that. So instead, I'll just randomly choose points at uniform in this matrix that I multiplied with. And because it's the data distribution that I got this matrix from, I'm assuming that it's sort of IID over what I would get if I would actually multiply with that matrix. Now, if you do that, you don't get the correct answer. And you can't run conjugate gradient because it's not the correct thing to do. You get sort of a noisy answer. How do you do that? Well, you want to introduce noise in conjugate gradient. And the one way to do that is to interpret conjugate gradient as a probabilistic method that has, now it doesn't get deterministic observations anymore, so the likelihood is not a Dirac delta anymore, but it just gets to see Gaussian observations of matrix multiplications. That might be a way forward for a fast matrix inversion algorithm. So now everyone's free to steal this idea and run away with it. But we'll see what it works on.
Video.
It's on video, yeah. Oh, damn. Shouldn't have mentioned this. Okay, good. So very quickly, now what's the nonlinear story? I talked about this last year, so I'm going to go through this very quickly. And obviously I have to do it because I have to talk about Gaussian processes, not just about Gaussian distributions. Now, classically, and this is my current picture of what's going on, well, how people built these nonlinear optimization methods in the 60s, 70s, 50s, so conjugate gradient was in the 50s, BFGS was in the 70s, is they essentially just took the existing linear solvers and just applied them to nonlinear problems repeatedly and just hoped that they work. That's more or less it. And then they write lots of cool proofs showing that they somehow work. There's something interesting about them. It's not a silly idea because you can prove that it does something meaningful. For conjugate gradient, you just keep doing the conjugate thing. For BFGS, you just keep doing the estimate in the Hessian thing. That gives you two different algorithms, but they come from the same source. But they're both still linear. They're sort of parametric regression, if you like. But you're actually learning a function, the Hessian of the objective function, which is not a linear function. It's a nonlinear function. It's just a function that returns a matrix at every point in the input domain. Now what you'd like to do is to do this properly, right? To actually model that this function you're learning has more degrees of freedom than just a matrix. And you can do that with Gaussian processes. And this is sort of actually one of the first things we did when we began to understand these methods, weirdly, because we could do that before we could understand the linear methods, actually. Here's this idea again. I've already shown you this plot, right? Now I'm just sort of turning the argument around. So if you have a Gaussian process belief over some function, and somebody tells you what the integral over that function is, so that's the other way around, right? In the quadrature example, I told you, if I get to see the function, I can tell you the integral. Here's the other way around. If you tell me the integral, so if you tell me that these four numbers are like this, then I can give you a Gaussian process posterior over the function, because Gaussians are closed under linear maps. So as we observe our line search directions in an optimization problem, so as we observe, do I have this? No? So as we observe, why do I not have this? This functional observation, y is equal to bs, that's obviously not actually correct. That's a second statement for non-quadratic functions. Sort of saying, this is the gradient. I've observed the gradient at 2 points. And this straight line through it, that should be b, right? Now what it really is actually is y is the integral over b along s. That's what the difference between gradients is the integral over Hessians, right? Now, in a Gaussian process model, you can actually encode that. You can say the thing you got to see is the integral over the Hessian function that we're actually interested in. The line searches are differences between gradients. And then you can use that to construct a non-parametric version of BFGS, essentially, of these Quasi-Newton methods that gives you a non-parametric posterior over the Hessian. And the additional computational cost of doing that is relatively limited, because it's the same kind of structure that we had before, but just now we don't have to just evaluate floating point numbers, we have to evaluate kernel functions first and integrate them, which you can do in closed form for certain kernels, like the square exponential. What that gives you is a method that can do sort of the following thing. Here's everyone's favorite optimization problem, Rosenbrock's banana. This is a two-dimensional function, x1, x2. Here's the minimum, somewhere down here. Every optimization method in the world has to start up here for all purposes every time it gets tested. And then it has to run into this valley and then run around here and find this minimum. Because it's a 2x2 function, or a function with 2 inputs and 1 output, its Hessian is a 2x2 matrix everywhere. So it's a function that assigns a 2x2 matrix to every point. That has 3 degrees of freedom because it's a symmetric matrix, right? 2 of those 3 are boring functions. They are not that interesting to look at. They are constant and linear. The third one, that's the second derivative along this direction, is an interesting function. It's a quadratic function. This is what this looks like. So this plot is the second derivative of this function in this direction. Now, the optimizer who learns the Hessian should, among other things, also learn this function. And now what I'm showing you down here are the posterior mean and posterior covariance of our non-parametric Gaussian regressor running within a Quasi-Newton method. This is the mean, and it has the exact same color scale as this up here. And as the algorithm gets to see more and more line searches, you notice that this function converges essentially to this function. Sort of roughly around here, everything is fine. Of course, it doesn't converge everywhere because it only got to see certain parts of the space. There are some parts where the prediction isn't quite correct yet. And this is the posterior uncertainty, and it reflects this property. So it sort of says, these are the regions that I went through. As I got to see certain areas, now I know what the function should look like in this area. Up here, I'm really uncertain. Up here, I'm really uncertain. I'm really uncertain. So it's a method that, while it runs an optimizer, can tell you what it thinks the function is trying to optimize look like. You can use this for various kind of neat functional generalizations of these methods. Let me just quickly look at the watch. Among other things, you could have evaluations of the gradients with noise. This is a problem that people have when training neural networks, where they currently do stochastic gradient descent. So this is something we're beginning to address. I recently wrote about this. You could think about optimizing functions that dynamically change while you optimize them. This is something the roboticists have. This is an ongoing project in Tübingen with some roboticists. You could also now evaluate gradients anywhere in the input domain, if you like. You can just run away and just evaluate wherever you want, because now we have a regression method that tells you how to use these evaluations you got anywhere. So now you could build parallelized optimizers, if you like, that just run around and find gradients in interesting locations and not just along the line searches. Various sorts of other tricks as well. Okay, we're still, in this area, the interesting questions are, we do not really know yet how to replicate the nice posterior uncertainty structure of BFGS in a natural way. Mostly because it's just a little bit more challenging, because now we're searching in a non-parametric space, not in a parametric space anymore, but we're beginning to make progress in this area. Okay, now I have 15 minutes left, and I'll be very quick, which is good, because what I'll talk about is something that we understand a lot less than optimization, and it's in many ways much more hand-wavy than what I talked about in optimization. Maybe good for you, because you get to see more plots and less maths. I just want to be very clear. Sort of, I'm going to be talking about something that many people hold very dear to their heart, and which is sort of considered as one of the largest, best successes of numerical mathematics in the past 100 years, solving ordinary differential equations. So I'm going to sort of trample on the graves of Runge and Kutter a little bit by talking in a really simplistic way about their very cool methods. So what I talk about is solving ordinary differential equations. So just to refresh your memory, an ordinary differential equation is a function, or no, it's an equation obviously, of this form. So there is a curve x which runs from a starting point to an end point, and we want a curve which fulfills everywhere the property, it's parameterized by t, and I want the property to fulfill to be that the derivative of x along t, like as a function of t, should fulfill a particular differential equation. Now, how do you solve an equation like this? Now I put it over there. So again, sort of, let's forget about the fact that there's 100 years of math behind this. Let's say you're sort of a high school student, you'd like to solve this problem. Here's a one-dimensional differential equation. This is t. I want to know x along t. Typically, these things are set up as so-called initial value problems. So you know that x of t0 has a particular value. You know x0. Now you could use this x0 to evaluate f at t0. That gives you an observation of the derivative of x at that point. Now you could extend this linearly forwards in time to t1. Use this sort of as an estimate for what f should be, what x should be at that point. You just sort of linearly extrapolate. You pretend that that's the right estimate. Plug this into f again. That's an observation y, because it's not actually quite the right thing, because we made an error by just linearly extrapolating here. That gives you a new observation of the gradient, and you can repeat that process over and over again to sort of get an approximate solution for a differential equation. This is called Euler's method, and it's maybe the oldest way of solving a differential equation. Now, there is a much more powerful framework for doing this, which is called Runge-Kutta methods. This is Professors Runge and Kutta. And it's slightly more complicated, but actually, when you think about it, it turns out to be quite similar to this kind of idea. It's a repeated process. I don't even need the pen. I can just point at things. It's a repeated process where you begin to evaluate at x0 and t0. That gives you a y1. You use that to construct a new estimate for what the correct solution of the ODE should be. And you construct that estimate by just adding to your initial estimate the thing you got to see in a certain way. Then you evaluate f at a new location, which you choose in a particular way. That's this new location. You construct a new estimate for x, plug this in. That gives you a new evaluation of sort of your approximate solution of the ODE. Now you repeat this process over and over again, and at each time point, you construct an estimate for the solution of the ODE, plug it into the ODE, and get an evaluation. And the way you construct this estimate, and that's the interesting trick. Am I again using the wrong one? No? Yeah. Oh, they both don't have these things in. Now, if you do this in this particular, so the first thing to notice, and maybe I should go forward. The first thing to notice is that the way you construct in all Runge-Kutta methods these estimates for the solution of the ODE, this is this thing in here, is in a linear way. So you're at time t, your approximate solution for the ODE, so estimate for what the solution might be, is a sum of the initial value and then the things you got to see, the observed sort of derivatives, approximate derivatives, with linear weights in front of them. It's a linear extrapolation method. So even though you might have heard of Runge-Kutta methods as this very elegant, sort of complicated thing, really what's going on is linear extrapolation. You get to repeatedly observe approximate solutions to the ODE, and you linearly combine them to get a solution, approximate solution to the ODE. Now, that sounds a lot like Gaussian process regression. And that's actually my entire argument. It's very lame. I'm just saying, these things are linear extrapolators. We know how to build linear extrapolators. They are Gaussian processes. So somehow there should be a connection. And I'm completely aware that this is a very shaky kind of statement to make. Why? Because so I'm going to tell you in a second how we can use a Gaussian process to construct a similar algorithm. But first I have to tell you why Runge-Kutta methods are actually cool. And the reason for that is that what these methods give you is after a certain number of steps, typically it's something like 4, 5, or 6 steps. In this case, it's 4 steps. You evaluate 1, 2, 3, 4 times. They give you an estimate for the solution of the ODE at a new location, which is sort of 1 step length h away from the initial value, such that the difference between the true solution of the ODE and the estimated solution of the ODE is a function which is of high order in the step length. In fact, in this particular case where we've evaluated 4 times, it's of 5th order in the step lengths, and therefore these methods are called 4th order methods, because the errors that cancel are of 4th order. And because h is a small number, you could think of it as a step length. It's supposed to be a small number. This is a good thing, because it means that this number is very small. So that's really cool, and it took 50 years of mathematical research for people to show that there's a general class of algorithms of this form, not just this one, but of general form, such that if you evaluate n times the ODE, there is actually an estimator which has a convergence order of n, essentially. And finding those is entirely non-trivial. It's very, very hard. And here's an example of a real Runge-Kutta method. This is what people use. This is called the Dorman-Prince pair. I don't actually know why it's called Dorman and Prince, because it was, I think, implemented by Hera and Vanner. And maybe they have those numbers from those people's paper. This is the same kind of table as this one. This is called a Butcher tableau. And this contains the locations where you evaluate in terms of step length, the weights you use to your previous evaluations to construct the next iterate estimate for where to evaluate the ODE. And then in the end, this is one rule of combining these resulting numbers together in a regression algorithm to get an estimate for the solution of the ODE. Now there's something really cool about this particular method, and that is that you can also combine these numbers in a different way with different weights. And you notice that there are really weird numbers in here. And then both of these are estimates for the solution of the ODE. It just turns out that this one is a particularly good estimate. It's of 6th. Well, it's the difference between the two solutions and the estimated solution is of order h to the 6th, so it's a 5th order method. And this one is slightly worse. It's a fourth order method. Now you could subtract these two from each other, the fourth from the fifth one, and then this one gives you a good estimate for the solution of the ODE, and the difference between the two gives you an error bar for how wrong these two solutions are locally to each other. And this error bar is then of fourth order. So you have a solution of fifth order and an error of fourth order, which is why in MATLAB this method is called ODE 4-5. And I'm sure many of you sort of start nodding because you've seen this thing before. So this is how what these methods look like in real implementations, and this is really tricky, right? So essentially what we're looking for now is a Gaussian process model which magically gives us these numbers. And this is Michael's PhD thesis, by the way, I'm talking about. And we already know it's very hard to get these numbers right. Not because we found it out, but because people have thought about it very hard. And they have very, very elegant theories that tell you how hard it is to find these numbers. So for the moment, let's forget about finding these really great numbers. And let's just say, well, how would we just find some numbers that don't have these nice properties, but are just interesting to interpret? Here's how you would build an ODE solver from a Gaussian process. And it's actually not our idea. It's a relatively old idea that maybe was first formulated by John Skilling in 1991. It was readily ignored, more or less. It's only become recently more interested, people have become interested in it again. Mark Girolami and some collaborators, and actually I think he was working with John Skilling a little bit at the time, have started to look at this again just last year, and their paper isn't even out yet, it's on the archive around the same time. So then Hauberg and I also worked on, sort of started out from John Skilling's paper and sort of worked in this direction. Our two answers are sort of quite orthogonal. They did a more mathematical analysis. We made colorful pictures that I can show you now, which maybe help us a little bit understand how these methods work. So we're starting with a Gaussian process prior over curves that might solve a differential equation. I showed you on Monday, and in the parametric case, an example of how you can use a Gaussian process to build a belief over curves. You just have different Gaussian process beliefs over each dimension of the curve's outputs, essentially, right? And if you wanted to solve a boundary value problem, this is the example I show here. So we're looking for a curve which goes from this point to this point. In this particular case, the application is we're trying to find the shortest path on some Riemannian manifold. You don't have to understand that. It's just a smooth curve which goes from here to here and minimizes some particular objective which is defined in terms of a differential equation, an ordinary differential equation. Now you would have a prior for this curve, a Gaussian process prior, which has a mean that goes from here to here, and a prior covariance that gives you kind of samples like this. And now we replicate the process that Runge-Kutta methods essentially do, just without the smart numbers. So we say, okay, I'm going to evaluate, let's say, at this point. Because I just randomly chose out of a point, a grid point to evaluate at. Now I need an estimate for the solution of the ODE at that point. I could get that estimate from the GP. For example, I could choose the mean. So I could say my current estimate for the solution of this ODE at this point is just the mean that I currently have. Now I could plug this mean into the ODE. That gives me an observation, y, which maybe says the curvature is sort of something like this at this point. Then this means I have observed the derivative of a function. And that's a similar situation to the one I mentioned before in quadrature. I get to observe the derivative. I would like to know the function. That's the same as observing the function. I want you to know the integral, right? It's actually the exact same problem. So I can plug this in, this observation y, to update my belief about what the solution for x should be. But I have to say this y, of course, is not the correct solution for the ODE because I just estimated what the true solution for the ODE should be. So I made an error when I evaluated this. This y is not x dot. It's just somehow has something to do with x dot. So I need a likelihood that tells me how wrong I am, how wrong this observation of y was. And one way to get that error bar is to say, well, I know I have a belief over how wrong this x hat was because I have a prior uncertainty over the curve. And I can propagate that prior uncertainty through f by some linearization or by some bound on the derivative of f to get an error bar on the evaluation y. And that's it. So now I just iterate. I repeatedly plug in points on the grid, evaluate the ODE at the mean with an error bar constructed from the prior uncertainty. And if I keep doing that, I'll eventually get a posterior over the solution of the ODE, which converges to hopefully a good answer. And there's a proof in this paper that argues that under particular assumptions, this is actually a consistent estimator, so it works. Okay. Very quickly, of course, all the nice properties of Wong-Kutta methods don't carry over, but the algorithmic structure carries over. It's the exact same kind of things you do with numbers. So all the other, like everything that people know how to do with Wong-Kutta methods, we can just sort of naively plug in. We can do implicit methods, we can do step size adaptation, and things like that. But we can also do new things that, and that's the reason why we would be interested in this whole thing, that you cannot do with Wong-Kutta methods. For example, and that's where the circle closes and we get back to where I started the talk, we can build a numerical solver for ODEs which can deal with uncertain inputs and uncertain outputs. So for example, you could ask, in this particular case, we've asked the solver to solve 5 different ODEs. The yellow lines are the solutions from Norman Prince, from ODE 4.5. The red lines are the Gaussian process posterior mean for this solver, and the green lines are draws from the posterior. And what you notice is here and here you don't see any green lines, or almost no green lines. Why? Because this method automatically adapts its uncertainty about the solution. It sort of finds that this is a simple kind of thing to solve. I basically know what the answer to this ODE is, so there's a very certain kind of path of solutions. This one is a really challenging ODE. I don't actually know what the true answer is. I'm still very uncertain about the solution. That's a nice thing to have. It's something that Wong-Kutta methods, well, they can give you an error bar at the end, but they can't give you a structured error estimate like this that you can draw from. Nothing that you can marginalize over or sort of use in your computation afterwards. So that's quantifying the uncertainty that the method injects. You can also start with an uncertain initial value. For example, here we're trying to solve a boundary value problem where one end of the boundary value problem is only known up to some Gaussian uncertainty. So we don't know where those curves are supposed to end. We only know that they have to end somewhere over here. But because the entire formulation is Gaussian regression, that's not hard to do. You just have observations in your Gaussian formulation, just somewhere in here, there's terms showing up that have a slightly larger uncertainty, and that's it. It's relatively straightforward. So that's a numerical algorithm which quantifies its own uncertainty and can deal with the fact that the inputs might be uncertain as well. Of course, by the way, that ODE that you hand in, that f, might itself be a Gaussian process. It doesn't have to be a well-defined function because we know how to deal with uncertain functions. So that would be a stochastic differential equation, and it fits into this framework really well. Is this a meaningful thing to do? Well, so you could wonder, okay, the Wong-Kutta methods have been studied for over 100 years. Maybe we can do new things that the old things couldn't do, but can we even do the old things right? So does this even work reasonably well? Because we don't have these nice theoretical guarantees that Wong-Kutta methods have. So here's only one anecdotal empirical evidence for the fact that what we're doing here actually makes sense. What I'm plotting here is we did essentially these kind of experiments on a slightly more interesting data set. It's the MNIST data set, and not this one, but the experiment that we did this on. We found some geodesics on all, like the set of all numbers 1 in the MNIST data set. Each of these green points in this plot is one ODE that we solved. We solved it once with Wong-Kutta with ODE 4.5, so that's sort of the best guess gold standard solution. And then these curves have a certain property that's called the length, which you can compute for geodesics. So that's a one-dimensional object you can look at, which is why we plot it here. And then we also plot the same quantity for our solver, for the solution that our solver found, or that this Gaussian process solver found. I'm not going to call it John Skilling's solver because I think we're doing it slightly differently from what John did. And if ours doesn't work, it's not John's fault. So sort of our implementation of this method. First thing, you notice that these points tend to lie on the same diagonal line, so they're roughly the same. That's good. They're not always the same. Sometimes our method overestimates the solution a little bit. It's too bendy, basically. But when that happens, the posterior uncertainty also becomes larger. So this method is sort of aware of the sloppiness of how imprecise it is. And notice that this is not sort of just a general property. So sometimes up here, here's that little curve where the method is actually quite certain about what's going on, even though it's one of the most challenging curves. It's sort of somewhere in the far corner over here. Okay, so this works relatively well. It turns out it can actually be very fast as well. So in this plot, I'm showing the same data points, these green dots, now as red dots, and I'm plotting the computation time spent in this and this method. So on this axis, that's the GP solver. On this axis, this is the Wong-Kutta solver. And this axis is scaled by a factor of 5 over this axis. So this line here is equal time spent. This is Runge-Kutta is 5 times slower than our method. This is 10 times, 20 times slower. And you see that most of these points are sort of in this area up here, where this method takes about 5 to 10 to 20 times longer. Why? Because we just gave our algorithm a fixed computation time budget. That's something that's very hard to do with Runge-Kutta. And with a GP, you can do it. You can just stop after finitely many points and just say, well, what's the solution like and how uncertain are you? So that gives you an algorithm which can sometimes be very fast and just at a price of sort of increased error, but a quantified increased error, which you can then sometimes just integrate over. So if you only need a very simple solution to an ODE, for example, in this Riemannian statistics application, you need a solution to thousands of ODEs, and we just use these thousands of ODEs to construct one simple gradient that we didn't just follow for one step and then repeat the whole process. You don't care so much about numerical precision. You want to have an algorithm that's fast rather than super precise. This is a kind of method that allows you to do that in a similar conceptual way to how conjugate gradient allows you to approximately solve a matrix if you don't have the time to fully solve it. Okay, with that, I'll wrap up. That was my example of ODEs. The overall story is we're beginning to understand numerical algorithms as inference algorithms. So methods that estimate something that you cannot directly observe. That's interesting because it helps us build better numerical methods. It's also interesting for machine learning and statistics because it helps us to build custom numerical algorithms which fit into the framework of probabilistic inference, algorithms which speak probability, which can deal with uncertain inputs and which can quantify their own finite time computation error and then return uncertain outputs. I showed 3 different examples: quadrature optimization and solving ODEs. Quadrature is in some sense a simple, from the GP perspective, a simple problem because there's a very direct connection. Integrating is just an analytical process in GPs. The challenging bit here is to get good models for functions in which you have sort of non-linear kinds of information. For example, where you know that the function is only positive. In optimization, I think we have at the moment the clearest theoretical picture. We're understanding that Quasi-Newton methods, BFGS, and conjugate gradient can be derived in a relatively exact way for a probabilistic argument, where there's all sorts of interesting design decisions going on, matrices being chosen such they are diagonal, such that inference is cheap, similar in spirit to how we choose Wiener processes to get Markov type fast updates, if you like. Because I have to say at some point in my talk that obviously Simo is going to cover this all tomorrow. We also have here interesting functional generalizations to non-parametric formulations that give you a more powerful framework for doing nonlinear optimization, which we have nowhere near properly explored yet. In the ODE world, the statements are still much, much vaguer. We're just making a simple, almost banal observation that Runge-Kutta methods, which are the state of the art in some sense for solving ODEs, are linear extrapolators. And we know how to do linear extrapolation with GPs. So now the hard question is trying to understand how these methods connect sort of in a harder, more precise way. The design criterion for all these probabilistic interpretations is quite different in numerics to what we usually do in machine learning. We're looking for methods here which are fast, just as well as they have to be well calibrated and robust. So we can often sort of be restricted to very hard linear algebra assumptions because these are the only ones we can actually implement in a relatively good way. And then that still means, though, that the resulting algorithms, even though they are probabilistic and Bayesian, are not necessarily slow. They are often just the exact same computational cost as the old methods with a tiny little bit of add-on to get your posterior uncertainty. There are lots and lots of open questions left that we haven't addressed in any way so far. You can also not download good implementations yet because we're still working on them. Here are 3 of the people working on this problem. This is my research group in Tübingen. This is Edgar Klensky. He was here in the summer for the GP summer school. He's an engineer working with dynamic control problems. This is Maren. She was also here in the summer. She works on the nonlinear optimization. She's a physicist. And Michael is sitting in the corner over there. Now he has more hair than when we took this picture. He has just started his PhD. He's going to work on the ODEs. So the reason I show this picture is, of course, because I'm really thankful to these 3 people for sort of trusting in me to do that this is a meaningful thing to do. I also really like the variance of backgrounds that people have who work on this. I think this is a super exciting area. We have relatively little mathematicians, so relatively little sort of adult oversight over what we're doing, which I think is a really good thing because it allows us to try out lots of crazy things that no sane mathematician would ever allow us to do. I find it's a very interesting area, and I hope I convinced you that it's a reasonably interesting thing to think about. Thank you. Thanks for saving me.
Okay, my main question, there may be a very simple answer to it, is that when you go down this route using the Gaussian process to solve all these wonderful problems, have you not still got the problem of having to somehow choose your covariance parameters?
Yes. And if there is a setting in which you don't know how to choose, if there's no way to choose your hyperparameters in a meaningful way, then I think our question is usually going to be, well, how do the established methods do it? Because they're solving the same problem, and we know that they are intractable problems. So there have to be assumptions somewhere in there. So either nobody knows how to do it, or there is someone who knows how to do it, and we just haven't realized yet how we can interpret it as a posterior uncertainty. In some cases, so we make statements about things that the classic methods do not make statements about. So the posterior uncertainty on the conjugate gradient solver, for example, is a thing that is new. It doesn't exist in the old methods. So there we are deliberately, we are injecting some additional assumptions, and then we're trying to be sort of transparent about the assumptions we make.
But I mean, for the ODE problem that you showed, you showed sort of a cloud of points which in some way seem to represent, to my eye, a kind of a known solution. Is that just handcrafted to get you off the ground and to show this?
So in this particular application, we are still choosing the hyperparameters in a very ad hoc way. And I think I should readily admit that. So you see that this method adapts its hyperparameters, which is the reason why this one is less certain, more certain than this one. So there is something going on. It's not just that it just sort of turned around a knob here until it looks good. So it's doing something, but it's completely true that there are still a lot of sort of design degrees of freedom that we don't know how to choose at all. And I think that's sort of Michael's headache. But there's also there's also sort of entire books about ODE solvers that we're only beginning to understand. So there's lots of choices that I think we can make in a much smarter way that we just haven't sort of really explored yet.
And do you see a future for this in PDEs?
Yes, so I know very little about PDEs, and I shouldn't be making any sort of much statements about them. I had some interesting conversations with numerical mathematicians who work on PDEs. My very hand-wavy takeaway is that it's actually easier to talk about PDEs because the standard solvers for PDEs are already sort of very patently least squares estimators. So in this community, people know that they do least squares regression essentially, so the connection is a lot closer. Runge-Kutta methods are in some sense harder, even though the problem is simpler, right? ODEs are simpler than PDEs in some sense, but they're harder because the theory is much more advanced. So there are these really strong statements about convergence properties that we don't have for PDE solvers. So competing with them is in some sense harder. Seymour.
So do you think that it would be possible to extend these Runge-Kutta things from deterministic to stochastic case? Because the stochastic Runge-Kutta thing is quite ugly.
Yes.
Can you repeat the question? There is like a...
So the question is there a way to do this with stochastic differential equations? And I think the simple answer is yes. If this f here, if this is a Gaussian process, which for many SDEs it is, so I think this is sort of the typical case for SDEs, then you're evaluating a Gaussian process. So there is some additional noise term here, which is Gaussian. And then this just slots in like a Lego brick in this description, and it's actually really straightforward. We haven't done that. Maybe talk to Michael. He might be interested in trying that out. But algebraically, I don't see a problem with that. What I don't know is how this compares to the existing SDE solvers. So I've spoken to some people who use SDE solvers, and I've heard very different kind of statements about how well they work. So there's some people who are adamant that they have very good solvers, and you are way too late to the game, it's all sorted out. And there are people like you who say, really, these stochastic solvers, I'm not sure how well they work, and I would like to have better ones. So I don't know whether we're stepping into a cesspool there by trying that, but it might be an interesting thing to do.
I had a question about the optimization. You had a quadratic likelihood and the quadratic prior.
Yes.
Have you thought of having, looking at problems where there's some other kind of penalty term that of course maybe corresponds to another type of probability of a different prior?
Yes. So this is. So the nice thing about answering these kind of questions is that I can always sort of say there's this entire community of people working on stuff, and I can piss them all off by saying one wrong thing. So optimization is of course a huge community. They have conferences with 10,000 attendants, much larger than NIPS, and I'm sure there's someone who's tried just about everything before. So one thing in particular that's interesting, one thing that there's a lot of people in optimization are interested in and have to a certain degree solved are problems where you're optimizing an objective which consists of the sum of two terms, one of which is smooth and continuous, and you know how to and convex, and you can optimize it with BFGS, and another term which has a certain nasty property, so it's non-differentiable, for example, at some point, but only at finitely many points. So you sort of know something smart to do iteratively at this point, and then you rely on BFGS on the other side. So there are many I think a lot of the answers to these slightly harder optimization problems where you have non-differentiability somewhere, or L1 losses at certain points, involve iterating back and forth between BFGS and some specialized smart method for one subpart of the problem, and then going back to BFGS back and forth. Which is why it's so interesting to understand BFGS, because it's at the heart of these methods. What I don't know is whether someone has built or thought about building estimation methods based on something else than a Frobenius norm here. Mostly, I think, for the same reason that so we use these we have estimation methods with L1 losses here in machine learning. They're called the lasso. Right? And how do we solve them? Well, we run an optimizer on them, BFGS. So it seems like the way we solve this problem is by appealing to these methods. So if there were a method that could deal with it more directly, I think we would know about it, because the optimization people would have told us about it. And I guess the problem is normally is that it's just doing all of this. The reason why you do it all with quadratic losses is that the solution is then linear algebra. Just like we do Gaussian process regression, because then the solution is linear algebra.
What about methods who try to get rid of the Hessian, totally like scale conjugate gradients? Do they fit in there?
So, okay, so I don't know about scale conjugate gradients. I know about Hessian-free optimization. There are I don't know the entire literature, so I can't make a general statement. I know that there are some methods which are called Hessian-free because they either analytically know the inverse of the Hessian everywhere. Okay, that's boring. Then you can just do that. That's natural gradient, right? Or because you never actually evaluate the Hessian. You only ever evaluate the projection of the gradient through the Hessian, and then you use conjugate gradient to sort of solve this problem to get an approximate inverse of the Hessian without ever writing out the Hessian. So that's connected to this because conjugate gradient can be interpreted as a Gaussian inference algorithm. It's not connected to the non-parametric the nonlinear conjugate Quasi-Newton method or nonlinear conjugate gradient, because you're not actually estimating the Hessian. But of course you could now, I guess you could construct this an algorithm where you say, I'm going to run conjugate gradient in this Hessian-free way at each time step, and then it would probably be a good idea to reinitialize the new conjugate gradient with the previous solution, because it's not going to have changed that much. So then you can think about how you encode that in a Gaussian model, and I guess you could do something like this. But it's very hand wavy because, yeah. So that's your paper to write.
Other questions? So I guess one sort of final thought that occurred to me while Philipp was talking is, I think I tried to emphasize in the introductory talk that I think in general we do too much to blur the distinction between model and algorithm, and that separating these things conceptually is a good idea. And most of what we seem to do in machine learning, and I think in statistics as well, is you build a model and then you derive an algorithm.
But certainly I've been involved in doing this with trying to reverse engineer kernel methods to a probabilistic model. And I think it's very clear a lot of what Philipp's been talking about today is to take some algorithms and try and reverse engineer what the model is underneath it. And there's a lot of benefit to be had from doing that. You can find a lot out. So, you know, that's sort of going the backwards way from what we normally expect, take existing algorithms and think, well, is there a model underlying this? And what is that probabilistic model? And I thought that was a really nice talk, and I think we should thank Philipp again. So let's start again at 10 past.